All right, we are recording now, and I'm going to switch over to the document camera. Okay. All right, here's problem set number 18. Number 1 says that we've got a bicycle wheel with a given diameter of 27 inches with a mass of 2 kilograms, and we're told it's rotating at 120 RPM. Given a little bit of conversion there. Part A is, what is a moment of inertia? So remember, based on the topic that we talked about last time, we have a formula for the moment of inertia. That's its resistance to change in the rotational speed. So the formula for that is kmr squared. And the variable we use for moment of inertia is I. So we have I equals kmr squared. The mass m is given, and the radius we can find because we want to express it in terms of meters. That's the standard form that we use. The k value is the shape factor. And like we talked about last time, you have to look that up in a table. So it's in the slides, and we talked about those last time. So for a wheel that's loaded at the rim but hollow in the middle, we have a shape factor of 1. So that's going to be pretty easy. So our k is going to be 1. You have to look that up in the slides that I gave you last time. M is the mass, that's 2 kilograms, and r is the radius. We're going to square it. So you got to convert 27 inches into meters. So we have a conversion from inches to meters. Make sure your inches cancel out. And then you want to convert from centimeters into meters. So make sure your centimeters cancel out. And you get 0.343 meters for the radius. So now we got everything we need. Plug it into this equation. K is 1. The mass is 2 kilograms. The radius is 0.343 meters that we got from right there. And don't forget to square that. Also, don't forget your order of operations. You need to square this and then multiply it times that, and multiply it times that. Don't multiply this times this times this and then square it. That violates the algebraic order of operations. So when you do that, you will get a value of 0.235 kilograms times meters squared, which is kind of a strange set of units, but that's what it is for moment of inertia. So now that we have our moment of inertia, we can answer part B, which is, what is its rotational kinetic energy right now? It's rotating at 120 RPM. So how much rotating kinetic energy does it have? Well, we have a formula for that we talked about last time. It looks kind of like 1/2 mv squared, which is our general formula for kinetic energy, but this is rotational kinetic energy. So it's a little bit different. Instead of mass in 1/2 mv squared, we have the moment of inertia. And instead of just straight velocity, we have the angular velocity, and we square it just like in the other equation for kinetic energy. So our equation is 1/2 times I, moment of inertia, times angular velocity squared. And to get angular velocity, we need that to be in radians per second. That's the standard unit for angular velocity. So we're given the value of 120 RPM, revolutions per minute, revolutions per minute. We need to get that into radians per second. Well, we know that 1 revolution around a circle has 2 pi radians. So there's our conversion here to get into radians and out of revolutions. So your revolutions cancel out. And we need to get into per second, not per minute. So we need to do a conversion from minutes to seconds. Make sure your minutes cancel out. And now you see your units are radians per second. So multiply across here, and you get 12.566 radians per second. Now we've got everything we need to plug into our equation for rotating kinetic energy, 1/2 I omega squared. So plug in your moment of inertia from up here in part A, plug in your angular velocity from right here, square it and multiply across, and you get 18.55 joules. Remember, a joule is also equal to a kilogram times meter squared divided by seconds squared. That's another definition of a joule. Okay, so that's part B for number 1. And then in number 2, it says that that bicycle wheel increases to 150 RPM. So we're speeding it up. Maybe we're pedaling it, or I don't know, a hand crank or something like that, but we're increasing the speed. So obviously we're giving it more rotating kinetic energy. How much work was done on the bicycle wheel to increase its RPM? Well, work is just the change in energy, in this case, the change in rotational kinetic energy. And so what we're going to end up doing is finding the amount of energy it had initially, which is right here, and finding the amount of initial energy it had at the final state at 150 RPM, subtracting them, and then the difference is the amount of energy that we added, which is the work that we did on it. So we have our energy of the flywheel, the little F stands for flywheel, at time 1. Energy of the flywheel at time 1 is what we just calculated from right here in problem number 1, 18.55 joules. And this was our initial angular velocity that we calculated up here. We need to calculate our new angular velocity because that's going to go into our kinetic energy equation. So we do a conversion here, just like we did up here in 1B, converting revolutions per minute to radians per second. So once again, cancel out your revolutions, knowing that 1 revolution is 2 pi radians. Cancel out your minutes by knowing that 1 minute is 60 seconds. And you get the angular velocity at time 2 is 15.708 radians per second. So now we can calculate the energy, the rotational kinetic energy of the flywheel or the bicycle wheel at time 2, E sub F2, energy of the flywheel at time 2. It's 1/2 I. Notice the I hasn't changed. The moment of inertia doesn't change when you speed it up or slow it down. So I is still the same as it was in part 1A. And now we have the angular velocity at time 2, and we square it. And when you multiply that, you get 28.99 joules. So our energy of the flywheel at time 2 was 28.99 joules. Our energy of the flywheel at time 1 from up here was 18.55 joules. And so we subtract them. The difference is 10.44 joules. That's the amount of energy that we had to add to it to spin it faster, which is also equal to the amount of work that we did on it. And notice it's a positive number because we added energy to the system. We're giving energy input into the system. So it's a positive number. Okay, that's number 2. Then in number 3 is the last flywheel problem. It says that we've got a uniform solid disc. So it has a different shape factor than the bicycle wheel. And it has a radius of 50 centimeters, which is 1/2 meter, and a mass of 30 kilograms. And over 1 minute, its RPM decreases from 20,000 RPM to 10,000 RPM. So it's discharging. We're getting energy output from the flywheel. What was its average power output over the 1 minute interval? So we can calculate the amount of energy that it had at time 1 and the amount of energy that it had at time 2. And say that the difference between those two is the amount of energy that it discharged during that time. And then we can divide by the amount of time. And when we divide the energy by the time, that gives us the average power over that time interval. This is from the equation energy equals power times time. So if I divide both sides by the time, I will get the average power over that time interval. So that's what we need to do. We know our radius that was given as 50 centimeters, which is 0.5 meters. We know our mass that was given as 30 kilograms. Our shape factor, well, we're going to need that because we need to know our moment of inertia. So we're going to have to do that. And to calculate moment of inertia, we need our shape factor, K. And if you look on the slides, a solid uniform disc. So that's just like a disc shape that's not hollow in the middle. It's a solid uniform disc. The shape factor is 0.606. And so we also are going to need our angular velocities. both at time 1 and at time 2. At time 1, it was spinning at 20,000 revolutions per minute. So convert into radians per second, just like we did in number 1 and number 2, and convert from revolutions to radians and from per minute to per second. That gives you 2094.4 radians per second. And for the angular velocity at time 2, it's the same type of conversion from revolutions per minute into radians per second, and you get 1047.2 radians per second. We're also going to need our moment of inertia because that goes into our energy calculation. Once again, I, moment of inertia, is equal to kmr squared. We know all of these things now. K was our shape factor that we had to look up based on the fact that it was a solid uniform disk. It was 0.606. The mass was given 30 kilograms, and the radius was given, it's 0.5 meters, and we square that. And when we multiply that together, we get a moment of inertia of 4.545 kilograms times meters squared. Now we're going to use our understanding that the amount of work that it did is equal to the change of energy. So we're just going to take the final energy minus the initial energy. That's our delta in energy, change of energy. So we got 1/2 times the moment of inertia times the angular velocity squared, all for time 2, minus 1/2 times the moment of inertia times the angular velocity squared, all for time 1. Okay, so we plug in numbers. Notice the moment of inertia is the same at time 1 and time 2. That doesn't change. And we have our angular velocity. So this is our angular velocity from our calculation at time 2. This number goes to here. And this is our angular velocity at time 1. So this number comes from here down to here. So after that, we're just going to subtract. Obviously, we know our flywheel is rotating faster at time 1. So when we subtract time 1, we know we're going to get a negative number here. But that's okay. We know what that means based on our discussion last time, as well as all the way back in the first part of the semester. If we get a negative number, that means energy is being drawn out of the system. So it's discharging. In this case, we are discharging our flywheel, which is exactly what it says in the problem statement. So when we do this calculation, we're going to get kilograms times meters squared divided by seconds squared. And if you do the calculation, you're going to get a pretty big number. So you can do some conversion into megajoules, which is 1,000,000 joules. So it's going to be negative 7.476 megajoules. That's the amount of work that it did. So we're almost there, but it does ask for the average power output. And we know that energy equals power times time, or equivalently, work equals power times time. So if we just take both sides and divide by the amount of time, we'll get the power, the average power. So that's what I'm going to do here. This number comes down to here because that's the change in energy. And we divide by 60 seconds because it says it's 1 minute. I want to divide by 60 seconds because I know that a joule per second is a watt. So that will allow us to get into a standard unit of power. So if I divide these numbers, negative 7.476 megajoules divided by 60 seconds, I get negative 0.125 megawatts, which is fine if that's your answer. Or I did a little bit more conversion. I converted it into kilowatts by multiplying times 1,000, and I got negative 125 kilowatts. So what that means is that we've got an average power from our flywheel of 125 kilowatts, or 125 kilowatts discharging from that flywheel over that 1 minute. That's the average rate of discharge over that 1 minute. Okay. Then in number 4, we're talking about compressed air energy storage, CAES. And we've got a salt cavern. that is given these dimensions, and it can be pressurized to 120 kilopascal, and it asks how much energy can it store. Remember, the amount of pressure is always relative to atmospheric pressure. So what we're really interested in is the difference between the pressure in the cavern and outside the cavern, because that relative difference is going to give us our energy storage. So it's asking how much energy can it store? So that's just equal to pressure times volume. Just remember that pressure is, like I just said, a relative pressure between the cavern and the atmospheric pressure. So we got to get our volume, V. So just multiply those dimensions together that are given in the problem, and you get 150,000 meters cubed. The pressure is a differential pressure, like I mentioned before. So we've got 120 kilopascals. Remember, a pascal is a Newton per meter squared. A kilopascal is 1,000 newtons per meter squared. So that's our pressure inside the cavern. This is atmospheric pressure, as it says in the problem, outside the cavern. So our difference is 18.7 kilopascals, which is 18,700 pascals. And that is useful for us because we know that a pascal times a meters cubed is a joule. That's another definition of a joule. So I'm going to multiply the pressure that we just got right here times the volume that we calculated right here. And we get 2.805 times 10 to the 9th. That is a billion pascals times meters cubed. A pascal times a meters cubed is a joule. And 10 to the 9th, like I said, is a billion, which is a gigajoule. So our answer is 2.805 gigajoules. That's the amount of energy that can be stored in that salt cavern. Then number 5 is also about compressed air energy storage. And we are discharging the energy from that salt cavern through a turbine. We're producing electricity. And in that process, the pressure decreases from 120 kilopascals to 110 kilopascals in 90 minutes. So this is very much like number 3. This is really similar to number 3. We are going to calculate the amount of work performed, or the change in energy. Then we're going to divide by the amount of time, and we're going to calculate the average power output, assuming 100% efficiency. So we know there's going to be some losses due to thermal energy transfer and friction in the turbine, probably in the compressed air cavern itself. There'll be some leakage, but we can make an assumption that it's 100% efficient, and we can get kind of a maximum amount of power output. All right, so to do that, we're going to do something similar to what we did in number 3. We're going to calculate the change of energy, delta energy, divided by the change in time. Delta energy divided by delta T. That's going to give us our power. So we know that our energy, like we just did in number 4, the energy is pressure times volume. So if I was going to write this out more, I could write it out P2V2 minus P1V1. But I abbreviated it a little bit. I know the volume of the salt cavern is not changing. The volume is what it is. So I can factor out the volume, and I can take the volume times P2 minus P1. So the volume is a constant, 150,000 meters cubed, like we calculated in number 4. And then we have P2, which is 120,000 pascals, minus P1, which is 110,000 pascals from the problem statement. And then we're dividing by the amount of time. Once again, I want to get it into seconds because we have a term for joules per second. It's a watt, which is a standard unit of power. So I don't want to leave it in minutes. I want to put it into seconds. So convert 90 minutes into seconds. Make sure your minutes cancel out. And you're going to get 540 seconds. I didn't finish this calculation here, but you would get 540 seconds. So we're plugging all of this into our calculator. 150,000 meters cubed times what's going to be 10,000 pascals divided by what's going to be 540 seconds. And when you do all that, you will get 277,800 pascals times meters cubed, which is a joule per second. And a joule per second is a watt. So we would get 277,800 watts, or 277.8 kilowatts. You can leave it in watts or in kilowatts or in megawatts, whatever you want. They're all units of power. Okay, then number 6 is asking about a gravitational energy storage system. This is a kind that I think is pretty cool, with those rail cars with a locomotive that goes up the side of a mountain when it's charging. So it's building up its potential energy. And then when it's ready to discharge, maybe at 4 p.m. or something like that, it's going to roll down the mountain at a controlled speed. And in the process, we're going to convert that gravitational potential energy into electrical energy. So on the way up, we're converting electrical energy into gravitational potential energy. On the way down, we're converting the gravitational potential energy into electrical energy. Of course, it's in reality not going to be 100% efficient either way, but it might be worth it. Even though it's not 100% efficient, it might be worth it because you can use the energy at 2 a.m. You can convert it into a state to be stored, and then you can get some of it back out whenever you want it, at say 4 p.m. or something like that. So we're using a rail car system. It has a mass of 200,000 kilograms. The track is 5 miles long. It's on a 10% grade, which means that for every 100 feet of horizontal distance traveled, you go up 10 feet. And it asks, what is the energy storage capacity of this system? Here's some hints. So if you think about this triangle that is the mountain, this triangle, there's a horizontal distance and a vertical distance, and the hypotenuse of that triangle is 5 miles. So it clarifies that. And it also gives you a conversion from miles to kilometers. So there's actually different ways of doing this. I'm going to show you the way that I did it, which I think is probably the quickest way, I think, of doing it. But there are different ways of doing this calculation and slightly different ways of thinking about it. So what we've got this triangle, and we know that for every 100 feet of horizontal distance, we're going up 10 feet. So what I'm going to do in my method of solving this, I want to find this angle right there. And if I find that angle, I call it theta, then I can use that knowledge to find what I really need to find, which is the vertical height. Because we know that the energy for potential energy is the mass times the gravitational acceleration due to gravity times the height. So to calculate this, E equals mgh. That's the same formula you probably learned in, I don't know, 11th grade or 12th grade, something like that. To calculate that, I've got the mass. I know what acceleration due to gravity is, but I don't know what h is. It's not 5 miles. 5 miles is this hypotenuse right here. So I need to find this h. So there's different ways of finding that. You may have done it a little bit differently, but you should get pretty much the same answer no matter how you did this. So the way I'm going to do it is by finding this angle. And then once I have that angle, I can use that to find this height right here and plug it into this equation. So the way I'm going to find this angle is with a little bit of trigonometry. You may have heard of this mnemonic device before, SOHCAHTOA, SOHCAHTOA. That tells you that the sine for S, the sine of any angle, is equal to the opposite side length divided by the hypotenuse. The cosine, C, cosine of any angle, is equal to the adjacent side length divided by the hypotenuse. And finally, the tangent for T, tangent of any angle, is equal to the opposite side length divided by the adjacent side length. And that's actually what I have here, because I know if this is my angle, this is the opposite side length of the triangle. This is the adjacent side length of the triangle. So I can use tangent here to find this angle, because I know the tangent of the angle is equal to the opposite side length, which here is 10 feet, divided by the adjacent side length, that's the A, which in this case is 100 feet. So the tangent of this angle equals 10 divided by 100. Your feet cancel out. So then you can use the inverse tangent. That's on your calculator. That's the button that looks like this right here. Tan to the -1, that's inverse tangent. So what you're doing here is you're taking inverse tangent of 0.1 and you're finding that angle. So in other words, what angle, when you take the tangent of it, gives you a result of 0.1. That's what the inverse tangent does. What angle, when you take the tangent of it, gives you 0.1. And like we just saw on the calculator, it's 5.71 degrees. So that's how I found out what the angle here is. This is the angle of the incline. So I can use that over here in this triangle. I know the hypotenuse of the triangle is 5 miles because it told me that in the problem. And I know the angle now is 5.71 degrees. So now I can use a little bit more trigonometry to find H. I want to find H, and I know the hypotenuse, and I know the angle. So the trigonometric function that gives us a relationship between those three things, the angle, the opposite side, and the hypotenuse, is sine. Sine of any angle equals the opposite side length divided by the hypotenuse. So the sine of this angle equals H, which is the opposite side length. That's the height that we're going up the mountain, the vertical distance, divided by the hypotenuse, which is 5 miles. Now just solve for H. Everything else is known. So take both sides times 5 miles. Take 5 miles times the sine of 5.71 degrees. And you get H, this vertical distance, is 0.497 miles. Now I'm going to want to plug it into this equation, and I'm going to want to use metric units. So I'm going to convert from miles to meters. So I have a conversion from miles to kilometers. Your miles cancel out. And you can convert from kilometers to meters, and your kilometers cancel out. And now you are left with 800.4 meters. So now I can take that, plug that into our basic equation, mgh. We're given the mass in the problem. We know the acceleration due to gravity is 9.8 meters per second squared. And now finally we know h. We can plug in 800.4 meters. And when I plug all that in, I get kilograms times meters squared divided by seconds squared, which is a joule. And I'm going to get a large number. And if I convert that by multiplying or moving the decimal point, I will see that it is 1.57 gigajoules, which is 1.57 billion joules. All right, then the very last problem here, for that same system, we're going to calculate some efficiencies. We know that none of these are really going to be 100% efficient because there's losses in friction, in electrical losses, in the motor. There's going to be several different losses in this system. So it says that it uses 1.84 gigajoules of energy, that would be electrical energy, to propel the train up the mountain. What's the efficiency as it's charging? So in other words, that's how much energy it used to get up the mountain. How much potential energy do you have now? We just calculated that. So the ratio of those two is the efficiency of the charging of this system. So we have our general efficiency equation is how much energy do you get out? What's your results, your resulting energy, divided by how much energy did you have to put into the system? So in part A, our energy out, that's how much energy is actually stored in the system. We're putting in a certain amount of energy and we're storing a certain part of that energy. So as we're charging the system in part A, we had to put in 1.84 gigajoules. That's what it says in the problem. And the amount of energy that's actually stored, we just calculated in number 6, and that was 1.57 gigajoules. So that results in an efficiency of 0.853 or 85.3%. In other words, 85.3% of the electrical energy that you put into that locomotive will actually be stored as gravitational potential energy in the system after it's charged. Part B is kind of similar. It says that as it's going down the mountain and discharging, it's going to produce 1.44 gigajoules of electrical energy. So what's the efficiency as it's discharging? Well, here we're going to compare the amount of stored energy, and we're going to compare that to the amount of energy that we get out of it as it's descending the mountain. So our energy out here is given as 1.44 gigajoules, and the stored energy, that's the amount of energy that was stored as gravitational potential energy, is 1.57 gigajoules. So the ratio of those is 0.917 or 91.7%. So in other words, what that means is that of the amount of energy that was stored as gravitational potential energy, I'm actually going to get 91.7% of that out as electrical energy as the system is discharging. And then finally, the very last one, we talk about something called round trip efficiency. So that is the efficiency that you actually get through both charging and discharging. So when I'm charging, I'm putting in electrical energy. When I'm discharging, I'm getting out electrical energy. So what percentage of the part that I put in am I going to get out when I want to discharge the system? So to do that, I have to compare the amount that I got out, which was 1.44 gigajoules, compared to the amount that I initially put in. That's the electrical energy in, 1.84 gigajoules. And so when I compare those, it's 0.783 or 78.3%. So you can do it this way. Actually, there's another way to do that. You can also calculate this by taking the charging efficiency times the discharge efficiency, and you should get the exact same number within maybe some rounding error, but it should be really close. So like I said, this is the amount of energy that you get out, electrical energy out, as compared to the amount of electrical energy that you had to put in. So obviously it's not 100% efficient, but it still might be a good and valuable system because you can put energy in at a time when you have low demand on the system, the electrical system, and you can get energy out at a time where you have high demand, so it can supplement the system. So it's load shifting. It's shifting load from one time to another time. All right, so I will stop the recording and then see if anyone has any questions. I have to stop sharing first.